And today I'm going to talk about Introduction to Machine Learning. No, I'm just trying to flip it actually, sir. Oh, okay, so but before I go there, I would like to take a few minutes to first give you an introduction to the intelligent systems track. So I think the slide is a little messed up, but so as you see there, in the so we have three tracks as Professor Narahari has introduced in his talk. So we have the systems track, we have the theory track, and we have the intelligent systems track. So in this particular, before going to this talk, I'm going to talk a little bit about what we have in the intelligent systems track for the summer school. And we have talks in all the three tracks in this summer school. So first we have the foundational subjects, linear algebra, optimization, and probability and statistics. We have talks on all these three subjects. So these will give you the basic mathematical concepts that are required to understand in depth any of the other topics in the intelligent systems track. So in the actual intelligent systems track itself, we have Introduction to Machine Learning, that's the current talk now. Then we have Machine Learning 2, which will expand on some of the concepts of the introductory talk. And then we have a talk on probabilistic models, which will help you look at some of the topics that we have covered in the previous talk in a new light, actually, in a different perspective, using probabilistic modeling. Finally, we have talks on reinforcement learning and game theory. So I'll try to put these two talks in perspective through the rest of my talk, these two areas in perspective through the rest of my talk. So we also have some application-oriented talks. We have machine learning in practice that's being given by engineers in Google. We also have a talk on natural language processing later in the week. So let's get started. So why do you think I have this picture here? Okay. Yeah, so a little louder? Yeah, so how many of you have seen the movie Robo or Intiran? Lot of you, okay. So all of you know Rajnikant here. His name is Chitti in the movie. So we were actually hoping that Chitti could come and give this talk from a first person perspective. He's an intelligent system, right? But yeah, I don't think he's yet available. So I'll be giving this talk. So jokes aside, while Chitti is not yet available, we have machine learning embedded in a lot of applications in the background around us every day. So let's take a few examples. Let's look at a few examples. Before that, how many of you have had a course on either machine learning or artificial intelligence? A few of you, okay, about 50%. So for those of you who have taken the course, this is going to be sort of a refresher, and it's going to set the stage for the rest of the talks in this track. But you will definitely see something new that you will learn in this talk. Okay, so the first example is Google. So this is where most of us start our day, right? So a lot of us have Google as the home page. So if you type a query, say digital camera, Google shows you a set of results, search results. So what is the order in which Google shows you those results? How does Google determine which search results are the most relevant for your query? Right? So as a lot of you might be aware, the founders of Google came up with Google PageRank way back when they first founded Google. And this is what was a differentiator. This is what differentiated Google from other search engines, and the rest is history. So Google is what it is now because of PageRank, right? So another example is when you type in your search query, you see a bunch of advertisements. So how does Google know which advertisements are the most relevant ones to show to me? So how does Google guess which are the advertisements I am likely to click on? So another example is the stock market. So you can actually make money off machine learning, right? So if I know the stock prices of a particular stock, for say I've observed the stock price for the entire year, how do I predict what will be the stock value tomorrow? Right? And if I can figure that out, I can actually make a lot of money, right? Spam filtering. So how does your email application know which emails are important to you and which emails are spam? So if you use Google, how many of you use Google as your Gmail as your primary? So Gmail has 4 folders by default, right? So what are they? There's some promotion, social, primary, and forums. Yeah, so 4 of them. So that's just an extension of spam filtering where, okay, so how does Google figure out which folder it should put your email into? So it automatically puts them into one of the 4 folders. How does Google figure that out, right? If you look at this picture, how do you figure out, how does a computer figure out all the cars in this picture? So now you might notice that it's very easy for you to figure out all the cars in the picture. That's a trivial task for you. But if you have to describe to the computer how a car looks like, it would involve so many difficult rules. Just think about how you would describe to a computer how it should recognize a car. It is definitely a non-trivial task, right? It's definitely not easy. You will have so many different rules to specify that. So these are all examples of which it would involve some form of learning or the other. So not just these, and you have so many companies listed here that are very popular companies that are actually working on different applications of involving machine learning, right? So now let's look at what exactly is this learning I'm talking about. I'm going to go with the standard Wikipedia definition here. Arthur Samuel, who was a pioneer in the area of artificial intelligence, gave this definition. Machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. The ability to learn without being explicitly programmed. So what do I mean by this? Let's look at an example. So suppose I have all of you must be having cell phones, right? All of you must be having cell phones, right? So okay. So you have an application in your cell phone which actually looks up the phone number if you type in the name, right? So that's doing something useful. Is that, should I call that machine learning? No? Why? It's not learning anything. Okay, so you have put in some memory there. So you put a name and a number, So it put it in its memory, it has memorized that, and it's just looking up from there, right? So there's no learning involved there. Suppose I say, okay, sort the contacts by maybe the frequency at which I call them. Then even then I'm explicitly specifying a rule, saying, okay, I'm giving a very specific rule, and I'm just asking it to retrieve by that, right? So it's just a useful application. So now, for example, suppose I say the application can automatically group your contacts based on a lot of criterion maybe. So these could be the criteria. So what is the average length of the call to the contact, number of incoming calls and number of outgoing calls to the contact, then the time at which I make a call to the contact. For example, I might call my personal contacts when I'm at home and professional contacts during office hours. The location from which I'm making the contact, I'm calling the contact. So it could be from my office location or my home location. So based on all these things, maybe it just groups my contacts into 2 different groups. Is this learning? Yeah, so this is an example of learning. So I think all of you are fairly clear now what we mean by learning and what we do not mean is learning here, right? So just to summarize it, we want to say learning is not memorization or explicitly specified rules, but we want to automatically learn some rules or some sort of a model from data and use that to make some real world predictions or come up with some useful outcomes, right? So before going on to more details, why do we need this learning at all? So it's usually because of the inability of humans to completely specify rules for every possible scenario. So if I have say only like say 20 contacts, I can actually specify whether each of them is work or home. There's no big deal there, right? But if I have 500 contacts, it's definitely not feasible for me, right? So we have too much data, there are too many scenarios, and it's not possible to sometimes even explicitly describe the rules. So for example, in the car, in the identification of cars from the picture that you had earlier, it's very hard for you to specify all the rules to the computer, right? Instead, if you can give the computer a lot of examples of images that are cars and a lot of examples of images that are not cars and have the software automatically figure it out. That's so much easier, right? So let's put this in a framework. You have some data. You want to feed that data to a learning algorithm in some fashion. Now when the learning algorithm using the data, it does something with it, maybe it cooks it, comes up with a model. Now you give some new query instance to this model and it should be able to make a meaningful prediction out of it. So in the previous example, suppose I'm able to group my contacts into say home and work. If I'm given a new contact, it should be able to see which group this particular contact would belong to, whether it's home or work. From the rules, automatically it has learned on how to group these how to form these two groups, right? So let's look now at a toy example to sort of get a better understanding of this now. It is summer, and I'm sure all of you like mangoes, right? So suppose I have a set of mangoes. If you eat too many raw mangoes, you would get a stomach upset. So you're given a set of mangoes and you want to pick only the ripe mangoes, right? So, but you are all experts with mangoes and you can very easily differentiate raw mangoes from ripe mangoes. But what if you want the computer to do this, right? You want to come up with a software that will help you differentiate raw mangoes from ripe mangoes. And the way you do this is you give the computer a lot of examples of raw mangoes, you give it a lot of examples of ripe mangoes. Given a new mango, you want it to be able to specify whether it's a raw mango or a ripe mango. Okay, so before we do this, we have a problem. How exactly do you input a mango to a computer? Okay, so what kind of characteristics would you choose? Color? What is? What is? Softness, okay, nice. Smell, yeah. Yeah, so these are all characteristics that you could choose to differentiate between raw and ripe mangoes, right? So the idea is to encode a raw or a ripe mango through a set of attributes of the mango that we call features, okay? So we want to come up with a feature vector for every mango that describes the attributes of the mangoes that will help us differentiate raw and ripe mangoes. So in this particular case, let's take the attributes weight and color. Okay, so these are two attributes that I'm going to go with right now. So at this point I would like to make a comment that so these feature vectors are nothing but an array of some real number values, and they're nothing but points in some n-dimensional space. So for example, if I take weight and color, I get points in two-dimensional space, right? And linear algebra is a topic that helps you understand these vectors and the properties of these vectors and how they interact with each other, right? So we have a talk on linear algebra later in the week. We have a talk on linear algebra today actually. So we said, okay, we converted the mangoes to tuples of weight and color, and in the training data, we also give the computer whether the mango, each mango is raw or ripe. So the feature vector xi is followed by yi, which is the class label in this particular case. And the training data comprises of xi, yi, x1, y1, x2, y2, x3, y3, so on, each mango and whether it's raw or ripe. Suppose I take only the weight and not the color, and I plot stuff like this, okay? So in this particular case, the red indicates a ripe mango and the blue indicates a raw mango, and I plot the weights like this. We see that it's not possible to differentiate the mangoes just by the weights, because as you see, there are some red colors that are on the left and some blue colors that are on the right, and there's no clear differentiation between them, right? So if I take just the weights, it's not a good enough feature. But instead, suppose I take both the weights and colors that I talked about earlier, and I plot these two-dimensional points. This is what I see. So what do you see in this?
Clear separation.
Yeah, so there's a very clear separation between both of them. Or you could say, okay, there are two different, this two separate clusters can be formed, but there's a very clear separation between both of them, right? So if I can learn a separating boundary between these two classes, given a new mango, I can say which side of the separating boundary it is on and just determine whether it's raw or ripe, right? So that's how I would make a computer learn to classify mangoes. So to put this in more perspective, what I usually want to do is, in a learning algorithm, suppose I can express my outcomes, which are the yi's, the raw or ripe, as a function of the weight and the color, right, as a function of the xi's. So in this particular case, I said it's a into weight plus b into color plus c, which is just a straight line. Okay, I'm writing my y as a function of the x's, and then my objective is to find the best possible function that separates the two classes. In this particular case, the best possible straight line. So when I say best possible straight line, what do I mean? I want to find the a, b and c, the parameters of the straight line, in the best, to get the best possible straight line, right? So let's call theta as a, b and c, right? So where a, b and c or theta is the parameter, and I want to find the function, or rather I want to find the best parameter to give me a good separating function between the two classes, right? And how to find an optimal separator between the two classes is something that you need to know something about optimization for that, and we have a talk on optimization, right? But I will not get into details of how we are going to do that, but I just want to give you an overview of a lot of things in machine learning in this particular talk. So I will not go too much into details of how something is done. So as we said, we want to find a straight line separator. Now as you see, there is not one straight line separator, there are multiple straight line separators. And like we said, we want to find the best possible straight line separator using some criterion, and depending on the criterion, you could come up with like different definitions of best. So just to put everything in perspective, how do you train the classifier now? You take some examples of both ripe mangoes and raw mangoes. You extract some features, which is the weight and color, and feed to the computer the feature vectors and the corresponding class labels, and you train the model by learning the optimal parameters theta. Given a new mango, you again convert it into a feature vector, see which side of the separating line it is on, and you can figure out whether mango is raw or ripe. That's what we said, right? Okay, so I think now everyone has a fairly good understanding of learning. So there are different types of learning, and we'll briefly go over that here. We have supervised learning, unsupervised learning, reinforcement learning, and we have learning in the context of multiple agents. So what is supervised learning? Supervised learning is exactly the mango example. So we have training data, and along with the training data, we have the target outcome or the labels. So, and the rest of the framework is the same. So the data is fed into the learning algorithm and it comes up with a model, and you give it a new instance, it can make some prediction, right? So there are two types of supervised learning that we are going to see. We are going to look at classification and regression in this particular talk because they are the most popular forms of supervised learning, but by no means are these the only forms of supervised learning. There are lots of different forms of supervised learning. It could be ranking, or there could be a lot of different examples, but we will look at these two in this particular talk. So we'll first look at binary classification. So we look at classification when there are two classes. So an example of that would be what? Yeah, the raw and the ripe mangoes, right? So that's an example of binary classification. So we have data that consists of examples along with their corresponding class labels. So we have x1, y1, x2, y2, and x and yn, where each y is either 0 or 1, denoting one of the two classes, right? And our objective is to learn the best function that separates the two classes. And what we said is there could be multiple separators of the two classes, and we want to find the best under some criterion, right? And how to find this good separating line will be discussed in the machine learning 2 talk. But in this talk, I'm going to give you an algorithm, an intuitive sense of an algorithm that can find a separating line, okay? So this is an algorithm called the Perceptron. How many of you have seen this before? Few of you, okay, not many. So again, you can just look at Wikipedia to find the Perceptron algorithm, but I want to give you an intuitive sense of it here. So the Perceptron algorithm iterates, so it assumes that, okay, it starts with some separating line to begin with. We want to find a separating line that such that all the raw mangoes are on one side and all the ripe mangoes are on the other side. It starts with some line, not necessarily which separates both the classes, okay, some line as an initial point. Until all the data points are correctly classified, it does the following. So for each training data point, if the example is correctly classified, it does not do anything. If the example is incorrectly classified, it adjusts the current separator a little bit so that it is pulled towards that point. So the exact update is actually quite simple, and you will be able to find it in Wikipedia, but I'm going to show you intuitively how this happens through a set of diagrams. So suppose I want to find this line, okay, such that all the circles are on top of the line and all the crosses are below the line. Okay, this is a separating line and it does not look optimal by any means actually, right? So you could have another line that better separates the two classes in this particular case. But suppose I want to find this line. So the algorithm now proceeds by taking some line to begin with. So I have this line as a separating line to begin with. So for every misclassified point, so suppose I take that misclassified point, for this point, the line is pulled a little bit towards the point. Now suppose I take that misclassified point. Why is that misclassified? Because I want all the circles on top of the line and all the crosses below the line. And this particular cross is above the line, right? So this is an example of another misclassified point. So what happens? The line is pulled a little bit towards that point, right? So this goes on, and it has been theoretically proven that if there exists a separating line between the two classes, then this algorithm will converge to that separating line. And of course, I have not specified the exact update here. I just said it moves towards the line. So, but the exact update is quite simple actually. You'll be able to find that in any reference of Perceptron. So now I'm going to show you an animation of the same thing. How can I get audio louder? How can I get the audio louder? Okay. Okay, I can't get any. Okay. Yeah, just give me this. Yeah, thanks. No problem. Yeah, okay, so this was just an animation to show how this separation happens. Right, so this is pretty clear, I think, right? So now I'm going to show you another video, okay, that actually uses a classification algorithm to classify faces, so classify images of faces into male or female. Okay, that's also an example of binary classification.
In the 1950s and 60s, scientists built a few working perceptrons, as these artificial brains were called. He's using it to explore the
So I think it's not clear, right?
How the brain learns. This perceptron is being trained to recognize the difference between males and females. It is something that all of us can do easily, but few of us can explain how. To get a computer to do this would involve working out many complex rules about faces and writing a computer program. But this perceptron was simply given lots and lots of examples, including some with unusual hairstyles.
But when it comes to a beetle, the computer looks at facial features and hair outline and takes longer to learn what it's told by Dr. Taylor. Andrew Cruikshank's wig also causes a little heart-searching.
After training on lots of examples, it's given new faces it has never seen and is able to successfully distinguish male from female. It has learned. While promising, this approach to machine intelligence virtually died out.
So that was another example of binary classification. So you don't need to have two classes. You can have multi-class classification. An example of that is the digit recognition problem. So suppose I am given handwritten digits and I would like to classify them as between as either 0, 1, 2 or so on up to 9. Okay, so here's an example. I'm given lots of examples of 0s, 1s, 2s and so on up to 9s. Right? And my aim is when I'm given a new handwritten digit, I would like to figure out what digit it is. So how many classes do we have here? We have 10 classes. So the previous algorithm, the perceptron, the straight line that we learned will not work in this case as is because there are 10 classes. But the idea here would be to learn the boundaries between all these classes, and there are extensions available for this. So we will not go into the details of that in this particular talk. Okay? So this is about classification. So the next form of supervised learning that we are going to see is regression. Okay, so in regression, the data again consists of examples along with some real value targets instead of class labels. Right? So as an example, suppose you want to predict stock trends. So I observe the value of a stock price from say 1950 to 2010. And I want to predict what the value of that stock would be the day after that. So the stock price is a real valued quantity, right? So basically it could be 500.8 or 1000.2. I cannot say it's one of several classes. So this is an example of a regression problem. So again we have input data in the form of some xi, yi, x1, y1 up to xn, yn. But each xi is again a feature vector. So that part is the same. So it's a point in some m-dimensional space. And each yi, instead of being 0 or 1, it is now a real valued number. It's clear, right? Yeah. So now the idea is to learn. So again, we want to express the yi's as some function of xi. But what kind of function do we want to learn in this particular case? We want to learn the best function that approximates or fits the data as closely as possible. What do I mean by that? So usually what we do here is we want to find the function such that the distance between the points to that function is as little as possible. So suppose we want to again learn a straight line. Like in the case of classification, let's say we just are interested in a straight line. Right? Let's look at this picture. Suppose I want to learn a straight line. So I'm given these points, right? Maybe these are the stock prices at different points in time. So maybe X is the time and Y is the value of the stock price, right? So I want to find a line that best fits the data or best goes through the data. And the way I can do this is by minimizing the distance of each point from this line. And how I'm going to do this exactly is not something I'm going to again discuss in this talk, but I do want you to understand the difference between the regression task and the classification task. Right? In the classification task, I wanted to find the best separating function between two classes. Here I'm trying to find the best function that fits the classes as closely as possible. Right? The distinction is clear, I hope. Right? So, given a new point, what do? So suppose I want to find the stock price for a new day. So I just take the new point on x-axis and put it back on that line which I've already learned, and I would get the corresponding stock price which is predicted. And if I make a good prediction, I make money. Right? So again, this regression is going to be discussed in more detail in the next in another talk on machine learning. So I do not always have to learn a straight line. I could have any arbitrary function that I can learn. So in this example, for instance, I could try to learn a quadratic function, or it could be a higher order function, or it could be actually any function. There are really sophisticated methods to learn arbitrary functions for regression. Another real example for this would be okay. Oh, okay. Suppose I want to predict the amount of rainfall using some features like the temperature, humidity, pressure, wind, atmospheric stability, and so on. Right? So this could be another example of regression. So the rainfall is actually it's not a class, but it cannot be a class, but it's something like 31 centimeters or 35 centimeters, 32.5 centimeters. So it's again an example of regression, right? So we've looked at two forms of supervised learning, which is classification and regression. So now we're going to look at unsupervised learning. So unsupervised learning is very similar to what we have seen earlier. The difference though is that with the training data, you do not have any class labels or target labels. Okay, so everything else is the same. So given some training data, you give it to the algorithm which learns some sort of a model, and then you can give it another data instance, and the model can come up with some useful prediction for it. So we are going to look at clustering, which is a popular unsupervised learning technique, and there are several different kinds of unsupervised learning, but we will look at clustering in this talk because that's the most popular form of unsupervised learning that's done. Suppose I go back to the example of raw and ripe mangoes. Now instead of, so earlier I had given some examples of raw mangoes, I had given some examples of ripe mangoes, and also specified whether each mango is raw or ripe, right? Now suppose I give the same data to the computer, but I don't specify whether the mango is raw or ripe. So now if I plot these points, instead of having some green points and some red points, I don't have any color for the points. I just have a set of points, right? So now what can the computer do? It can cluster them. Yeah, so it can do something even without knowing the labels. So the computer can actually try to find two clusters. So let's look at a way of doing this. A popular clustering algorithm is the k-means clustering algorithm. How many of you have seen k-means before? Okay, about 50% of you. Okay, so suppose you are given some data points x1 through xn, and you want to learn the cluster membership for each data point. right? So the input is a set of points x1 through xn, and there are no y's here. And then the output is basically some z1 through zn, where each zi is the cluster membership. Each zi denotes which cluster the xi belongs to. Okay? So the idea of k-means algorithm is to find the most cohesive clusters. So you want the clusters to be as self-contained as possible. You want the clusters to be as cohesive as possible. So again, like in the case of classification and regression, we want to come up with some objective function that helps us to find cohesive clusters. Okay? And in this particular case, this objective function happens to be, I would like to minimize the distance of every data point to the center of its corresponding cluster. So I want to minimize the distance of every data point to its corresponding cluster centroid. And out of multiple cluster assignments, I want to find that cluster assignments that minimizes this distance. Right? That is my objective. And now, from that I can actually come to a very intuitive algorithm. Now, I'm not going to derive how we again went there, but I'm going to show you the algorithm itself. Some of you might know this. So, in the k-means algorithm, we randomly initialize some k points as the cluster centers to begin with. And iteratively we do the following. In step 1, we assign each point to the cluster corresponding to the closest centroid. In the second step, we update each centroid as the mean of all points in the cluster. So let me just show you pictorially what I mean by this. So in figure A, in this particular figure, I have a set of points and I can group them into two clusters. Right? So now I arbitrarily start with two cluster centers, the red cross and the blue cross. Right? So in step 1, what I do is I color every point that is closer to the red cross as red, and every point that is closer to the blue cross as blue. Right? In the next step, in the second step, I update the red cross to be the center of all the red points. I update the blue cross to be the center of all the blue points. Right? So again, I update every point that is closer to the red cross to be red. I update every point that is closer to the blue cross to be blue. And again, I update the red cross to be the center of all the red points and the blue cross to be the center of all the blue points. And as you see, in 2 iterations, I came up with pretty good clusters. Right? So this is k-means clustering. So now I'm just going to show you a video that shows k-means clustering in action. So there are 4 clusters that the algorithm is trying to find, and the algorithm starts with some random points as the cluster centers, and in course of time it actually converges to the right clusters. So it's the same thing that you're seeing for 4 clusters, right? So now I'm going to show you a video that shows you a real life application of unsupervised learning. So, so 3D scanning. So the next video shows you an example of 3D scanning where a scene is being scanned and being obtained as a set of lot of different points. So it's called a point cloud usually. The output of a 3D scanning algorithm is usually a set of lot of different 3D points. And the algorithm, the software here is trying to automatically figure out all the objects in the scene. And this is clearly a form of unsupervised learning because you just have the points. You're not given any other information to train what the objects could be, right? So scanning the scene at the top and it's figuring out all the objects by some form of segmentation. Okay. So now I'm going to test whether all of you are awake. So I have all these objects. What kind of clusters should I expect from these objects? A little louder. Fruits and boxes. Okay. I would expect fruits and boxes. Right? Can't I expect this? Can I expect this? Why? Yes, images with background, images without background. Right? So, okay, if I'm given these objects, there is no unique way of clustering them, right? So, there could be so many different clusterings that I can come up with. So, okay, if I run k-means on this, what clustering am I expected to come up with? Is that a little louder?
We need to have a class which defines which kind of cluster. It depends on feature vector.
Yeah, so it depends on feature vector. So all answers are sort of correct, but this is the most clear and straightforward answer, which is you need to define the feature vector correctly. And depending on how you define the feature vector, you get different kinds of clustering here. So in the case of mangoes, right, because we had given the color and weight or whatever, we could determine whether it's raw or ripe. So similarly, here we need to give some meaningful feature vectors to get the kind of clustering we want. So this also tells you how important basically finding the correct feature vectors are. So feature engineering is important. Okay, so we looked at supervised learning, we looked at unsupervised learning. The third type of learning is the reinforcement learning. So this is the picture for reinforcement learning, but I'm going to give you an example. Reinforcement learning is like training your dog. So how many of you have pets? Have pets? Okay, so if I want to throw a ball and I want my dog to go and fetch the ball, how would you train it?
Whenever it fetches the ball, you give it treats so that it understands its plan and what you want. Whenever it does what you want, you give it some sort of.
Right, exactly. So that's a good way of training my dog. So I throw the ball, and if the dog is going towards the ball, maybe I give it some biscuit. If the dog is not moving towards the ball, it's a lazy dog, maybe I beat it. Okay, I don't beat it, I put a sad face. Okay, so again I throw the ball. If the dog is going towards the ball, I give it a biscuit. If it's not going towards the ball, I put a sad face. So I keep repeating this, either biscuit or sad face every time. Okay, and ultimately at some point the dog would maybe go towards the ball and realize it's a good thing to go towards the ball because it's getting biscuits, right? And ultimately it learns that it needs to go to the ball and fetch it similarly. So the same thing is happening here. The learning algorithm is the dog and environment is everything else. So environment is me who's training the dog. So the environment, so I actually throw the ball and give a new state to the learning algorithm. The learning algorithm on seeing this, so the dog on seeing this, either actually it does some action which either goes to the ball or does not go to the ball. Based on that, I give some reward or feedback, which is either a biscuit or a sad face, right? And also I throw the ball again and give it a new state, so it again knows where the ball is. At this point, it can again react to it by actually going to the ball or not going to the ball, and this process continues. And finally, the dog learns to go and fetch the ball, right? So I'm going to give you example. So in the following video, you're going to see a robotic arm that's going to try to stop a ball. It tries to be a goalkeeper, right? So you would see that initially it is not going towards the ball at all. So in course of time, it actually goes towards the ball after some time, and finally it learns that okay, if it goes and stops the ball, it gets the maximum reward. So it actually learns how to stop the ball. So now it's at least going towards the ball. Okay, so this is an example of reinforcement learning. So we looked at supervised learning, we looked at unsupervised learning, and we looked at reinforcement learning. So now the last thing we're going to look at is learning in the context of multiple learning agents. So in all the previous forms of learning, there was one learning algorithm that was taking some input and doing something, learning something from it. So now if there are multiple of these learning agents, each learning agent wants to do something that maximizes its payoff. So each learning agent is a rational agent that is doing something to maximize its benefit or payoff. There could be multiple such learning agents. How do they interact with each other? Each learning agent would know that the other learning agents are also trying to selfishly maximize their payoff, right? So when there are multiple learning agents, it leads to a lot of different interesting problems. So let's show you an example of this in a video. So it will be very clear to you what the different learning agents are when you see this video. So there is something called the RoboSoccer that is held every year. Okay, so that's a multiple agent scenario. So there are many different problems that come up when you have multiple learning agents. Game theory is one topic that actually deals with this multi-agent scenario, and you're going to have a talk on game theory later in the week. So just to recapitulate what we have done, we have looked at supervised learning, and specifically we have looked at classification and regression. We have looked at unsupervised learning, where we did clustering. We did reinforcement learning, which was like training your dog. And we have seen learning in the context of multiple agents. So this is the end of the content of my talk, but the rest of the time what I'm going to do now is I'm going to give you a lot of examples, and you should tell me what kind of learning it is. Let's go back to organizing contacts, which we saw in the beginning of our talk. So suppose I have an app that automatically organizes my contacts into two groups based on a lot of things we saw here: average length of call, number of incoming outgoing calls, location and time of call, and so on. So Why is it unsupervised learning?
There is no tagging as such.
Okay. Yeah. So now suppose I change this problem slightly and say that, okay, you are asked to tag, say, 40 of your first contacts, yes, as work and home. So then what is it? Supervised learning, right? So now, music genre identification. So all of you like music, right? So you must have a lot of music on your laptops. And suppose I want all the music classified into, categorized into groups. So before going there, I want to mention one thing. So we have seen a lot of different kinds of data until this point, right? So we have seen images in the car identification problem. We have seen mangoes, and we have seen 3D scan data. So we have seen a lot of different types of data, and now here we are seeing music, right? So all the techniques that we learned until now are agnostic to the type of data. So because I can do classification, clustering, I can apply all these techniques to any kind of data. But what is it that differs between in my framework for different types of data? Right, feature engineering. So feature engineering is what makes is different for different types of data. So in this particular data, so I have a slightly more involved feature engineering. So I need to use some signal processing techniques to sort of get in each kind of music what are the prominent frequencies maybe, and I need to do some involved feature engineering, right? So assume you are given the features here, and you want to categorize the music. What kind of learning would this be? Why is it supervised? You can use a mic. Okay.
If we want that, if we say that it is a supervised learning, then first of all we have to provide it with the training data. If we are already having that this particular song is of this type, and by using that if the computer learns, then we can categorize it as supervised learning. And if we are not providing it with the training data, then I don't think it is possible to say that it is supervised learning.
Okay, so that's a good answer. So if you're not providing with any training label, so if we say that, okay, suppose we say that categorize the songs into classical, electric, jazz, pop and rock, given some examples of each type, then it is supervised learning. If not, we have unsupervised learning. So but in this particular case, I'm not guaranteed that the classes that I will get are actually classical, electric, jazz, pop and rock. I will get some classes. If these happen to be the prominent groups, then I would get it that way, but it is not guaranteed. But in the case of supervised learning, if I give you examples of all these 5 types, most likely I will actually end up getting all these 5 types. Okay, okay, let's see another example now. Finding topics in a collection of documents. So is any one of you into topic modeling here? No one? Okay. So suppose I have a bunch of documents and I want to automatically categorize them into some cohesive groups of, say, there could be topics like sports, politics, etc. What kind of learning would this be? Unsupervised. So how would you go about this? Any ideas? Right, so we could try to find the frequency of words in each document. So what we want to do, what we want to talk about is the feature engineering, right? So, you want to say something?
First of all, the computer must know what all words come within the particular field like sports. So after it only we can apply that, we can differentiate like the words of sports and then words of politics, and then
so you're absolutely right. So if I want particular categories like sports, politics, suppose these are my set categories, right? And I want to definitely categorize into these. There's no way I can do this well without giving some examples of these. Then it would become a supervised learning problem, and then I would get exactly categories like sports, politics, etc. But the best I can do when I don't have that is to try to find whatever groups I come up with. So the idea is, okay, if I had a lot of documents that are maybe sports and politics, most likely I'll come up with these 2 groups, right? So the most popular technique to extract features here is basically, suppose you have some 10,000 words in English vocabulary. Each feature vector is a 10,000 dimensional vector, and the value of a particular component of this vector is the number of times that particular word occurs in the document. And this is called, so there's actually a talk on natural language processing that does not deal specifically with this, but a lot of different ways of manipulating text. It talks about a lot of things that are done to pre-process text. So for example, I have a lot of words like a, and, the, and so on, right? If I don't remove these features, so it's good for me to remove these features because they don't contribute to any class, any category, right? So the natural language processing talks about a lot of different things to do with text, and how we also do a lot of interesting, what are the different interesting things you can learn as well, okay? Okay, next example. Suppose I'm a new user of Facebook. I've never seen Facebook before. And the first day I go to Facebook, I think, okay, Facebook is so exciting, let me upload my latest photo album there. So you know that Facebook automatically tries to show all the faces, different types of faces in each album, and asks you to tag them, right? All of you must have seen this, right? What kind of learning is this? Okay, you need to explain why, whoever is saying something.
Because the software does something and it asks for our feedback, which is tag. So we give a particular tag, then based on that, it will categorize.
Okay, so assume that, okay, fine, that's a good answer. Assume that all the people in my picture, in my album are new, because I'm a new user, right? Maybe my friends are also not on Facebook, so I'm a new user who's uploading an album. What then? Little louder. Why supervised?
You have initial photo which is known as static, so any other photo of this
Okay. Yeah, so okay, if the people in my album are already on Facebook, then okay, it has some examples. Suppose I have the situation where the people are not already in Facebook, right? Then it's unsupervised. Yeah. So if it knows some of the people, maybe it can use some supervised technique because it has examples of all these photos, right? Okay, so good enough, fair enough. Spam filter. So what kind of learning is this? So you're given some examples of spam emails and some examples of non-spam emails. You have to design a spam filter. Supervised. And what would your features be? Yeah, so exactly what one of you has said earlier. So you want to see what are the words that occur in a spam document, what are the words that occur in a non-spam document, right? I think that's exactly the answer someone had given for sports and politics earlier, right? So that's exactly what you want to do. And then the features would be basically all the words in the document. Okay, how many of you like cricket? A fair number. So how would you predict how much Sachin is going to score in a particular match? Regression. So what kind of features would you use? Who's bowling the ball? Okay, what else? Previous performance, yeah. The crowd, yeah, crowd is also an important factor. So you could have all these different features, right? Okay, so pretty much the last example. I'm given this image and I want you to identify all the cars. This is one of the first examples we have seen, right? Let's come back to this. So what kind of learning is involved here? So I'm saying I'm given lots of prior examples of cars and examples of images that are not cars. So why is it supervised? Okay, fine. But how do you identify where the objects in the image are though? Right, so you need some image processing here, but this can be thought of as an unsupervised learning problem. So you saw a segmentation, scene segmentation earlier, right? So you saw where a scene was being, all the objects in the scene were being recognized. So it wouldn't be such a simple thing, but still this could be looked at as a segmentation problem of finding all the objects in the image. So it's not exactly a segmentation problem, but this would be an unsupervised learning problem, finding where the cars are. And then what you said is right, given a car, given an object, to find out whether it's a car or not is a supervised learning problem. So what will be your features here to find out whether it's a car or not? Okay. Yeah, so what, repeat what your features are.
Height of the car, if you are specifying a car, so you can give the range.
So that's actually a slippery slope, right? So the car could be in the front, the car could be behind, there are so many different possibilities, right? So the height cannot always be a number plate detection. First you have to detect the number plate.
Actually, we can detect if the number plates are generally white, mostly, though there are some exceptions. We can look for colors, number plate colors, rectangular colors.
Okay, so this is actually, I want you to just think about this, right? So this is the end of my talk. I want you to think about what features you would give for this particular image, okay? Yeah. So, yeah, so all these photos are from Google Images, and there are a lot of people who contributed to getting the images. So I want to end this talk with the following note. So each of the topics that you saw in this particular talk, you can go into any depth and with good knowledge of linear algebra, probability and optimization. There are beautiful concepts involved in any of the topics that you have seen in this particular talk. And these are all active research areas that are going on in our department. But I also want to point out that machine learning is also a very application driven field. So it's a very data driven field. So I want you to look at www.kaggle.com. Being computer science students, all of you can go to this website and you'll find interesting problems. How many of you know about Kaggle? Few of you, not many. So, okay, you will find interesting problems right from binary classification, maybe like a spam filter, to actually there is a problem where you want to find the properties of Higgs boson, right? So you have a variety of problems on Kaggle and also a lot of pointers on how to get started with using some of these machine learning tools. So that's a very interesting place to go and see.
So,
yeah.
Any questions? Any of you? No questions.
No questions? I think everyone's waiting for the break.
Okay, so let's thank Lavanya for this talk. So, we'll take a short break now. Coffee and tea is arranged in the corridor. So talks will resume at 11:30. So all of you can join us.